Well guys, today I'll be focusing on the valid anagram problem and walking through how to get to the solution and just a good way to solve Leetcode problems in general. The task is to create a function that returns true if two words given are an anagram and false if they are not an anagram. In this case, we can see that anagram can be rearranged to get this other word just by swapping out the letters, and we would output true. And in this case, we would see that rat cannot be arranged to produce car, so we know it's not an anagram, so we would return false. And I'm going to show you how to get a really nifty, nice solution. So we know two words are anagrams if we can rearrange the letters. And with this logic, you might have come across the idea that we could actually sort these two words alphabetically, because if we're basically arranging the words with the same exact rule that works for all of these words, and if they are the exact same, that would mean that they are anagrams of each other. In this case, we could sort these two words alphabetically, and we would get APT for both of them, which would mean they are anagrams. And now this, for time complexity, will take O of n log n time. Now, I'm not going to explain how we got to this time complexity, because that has to do with the sorting algorithm itself. If you're not familiar with it, the fastest possible sorting algorithm is O of n log n time, which is slower than O of n time, but also a lot faster than O of n squared time. But let's try to think of a solution that's linear, that's in terms of O of n. And if you know about your time complexities, something that can be like 26n would still be in terms of O of n. So that can give us some other ideas. For example, we know there's only 26 possible letters, so what if we loop through every letter, starting with A, for each word, count how many A's we have. In this case, we would both have one, so we can continue. We would go through B, see that they both have no B's. We would eventually get to P, see that there's two P's. We would get to T by the same logic, and therefore we would know if it's an anagram. And now that would take a time of O of 26n, or you could even say it's 52n because they're going through these two strings. And because the rule is a big O notation, we can just remove the 26 altogether. But not all O of n's are created equally. While this does have O of 1 space complexity, as in we don't actually have to store additional items, we can create a way faster linear solution that makes it so we only have to go through these words once, so each of the words once, and then we can finally check if they're out an anagram after a constant operation. And when we go to constant operations, one that might come to your mind is a hash map. And let me draw this out for you. If you're not familiar, a hash map is basically a dictionary of key value pairs. In this case, I can keep track of a dictionary of the word tap and counts that we have 1 T, we have 1 A, and we have 1 P. And we can actually access each of these items in O of 1 time, which is obviously very fast. And we can also write to it in O of 1 time. And then we can do the same exact thing for our other one. We could count the occurrences of each letter and pat, store in a hash map, and we would get, in this case, the exact same thing. So we would get T, we would have 1 T, 1 A, and 1 P. And now, finally, something we can do with hash maps is that we can actually iterate them most of the time, I'm not going to say all the time, in O of n time, when n is the amount of elements in the hash map. And After we read through one of these dictionaries in O of n time, we can also check if the other dictionary has the same amount of a certain element. For example, we can check from one of the dictionaries if the other one has the same amount of T's, same amount of A's, same amount of P's. And if not, we can tell if it's not an anagram. If so, we can tell if it is an anagram, which makes it a very fast solution. It does have O of n space complexity, which is worse, in which we would have to make a trade-off. In this case, I think it's a lot better to study this O of n solution. I'm going to go show how you would code this, and hopefully that will make it easier to understand if I didn't explain it perfectly well in plain English. Okay, the first thing we need to do is make sure that both of our strings S and T are of the same length. Because if they're not of the same length, there's no way you could arrange the letters to be the same. In this case, we don't have to create an else statement or anything, because if it was true, we would have already stopped the program. And now we need to keep track of a dictionary for each of these string. So let's create a dict of S, and we'll just make it an empty dictionary, and a dict T, make that also a dictionary. Now we can loop through the characters of each of these. So we can start with, say, for C and S, and to insert it into the dictionary, I can say dict S of C. In this case, we're passing it in the key. And now this is a trick you can do in Python. I can actually say I want to get the item with the key C, but I also want to add a default case just in case it's not found, and this can be useful so I don't have to check if it already exists, because we already have a base case that it would be 0 if it would not be found. Either way, we just increment that and do the same thing for our other dictionary. And after all of this, we will have two dictionaries that will have something like there's 1A, there's 3C, something like that, but we'll have one for both. And finally, what we're going to do is we're going to iterate over one of these dictionaries and see if the amount of each key, as in each letter, will be the same for the other one. So in this case, I'm just going to ask if the dictionary of SC is not equal to the dictionary of T. We can immediately return false. After all of that, we return true because there were no mistakes, as in they were all the same and everything matched. So now we can submit this. Oh, and there actually is a small error in this because we don't actually have a default case for this. That's my bad. We want to default to 0, or else we'll just get an error. In this case, in Python, we would get an error because it wouldn't be found. But now it should work. And woohoo, we beat 47.25% of other people in speed. But more importantly, when we look at our complexity, we get O of n, which is exactly what we want. There's no faster than that in this case. I hope this will help you understand the problem more. Anyways, if you enjoyed this video, please give me a thumbs up. Hopefully you subscribe. Like always, bye-bye.